I want you to have a go at a gravimetric analysis where you take something and you mix the chemicals together so that one thing selectively precipitates out of solution. And there's a whole procedure about how to collect that solid and dry it and then let it cool and then test it again. There's a whole testing procedure around that. It might take more than might take a couple of weeks worth of lab time anyway. It's just good to be able to say that you've done it and that you understand the procedures behind it, because you have to, what we're going to end up doing is being really scrupulous that, you know, up to now, if you just pour something from this one into that one and you spilled a bit, doesn't really matter. Now it matters, but you have to get every last drop accounted for, okay? It has to be accounted for. If it didn't make it from here to here, I still have to know where it is. And, you know, if you've made solids before in the lab and you have to weigh the final thing, do you scrape everything out of the beaker? Do you leave a little bit behind and say, oh, that will do? In quantitative analysis, no, you need every last thing. So there's a whole bunch of lab techniques that you've been allowed to skate and not learn about. I mean, there's a correct way to pour from a beaker into another beaker that you've never seen. I've shown it to one person while I've been here, Peyton, who's graduated as chemistry last year, and she went, wow, there's a special way of holding the beaker that it won't spill. So we'll do all of that. Titrations sometimes feel like it's, hey, this is a reaction and that reaction has a finite beginning and end. And then other times it feels like, oh no, this is definitely an equilibrium, especially if it's a weak acid. Weak acids have equilibrium. And the things that we're going to precipitate, we're going to fall back on KSP. Remember KSP from chemistry 2? That was your solubility product. Yeah, I don't, it's okay if you don't remember, but we are going to remind you. It's kind of a limit of what the solubility is. And that's an equilibrium value. So we've got to start talking about equilibria. And we'll do that today, but we've got to finish up a couple of things about methodology and about errors. So we saw, I'm going to move these so I can use the whole board. We saw that the error that you propagate by adding or subtracting two numbers from each other followed a formula, right? Put that down because I broke the paper. Well, the formula, how did I write that? Did I just say error equals? Let me have a quick look at how I wrote it out, because oh no, that was something different. The very last thing we did is total resultant error, they called that. Well, you know what that really is, right? So I said for adding and subtracting that the total resultant error was equal to, what did I say it was? Yeah. Yeah. For each individual measurement. Is the square root of the error in A squared plus what the error B is squared. That's assuming that you're only adding two numbers together, A and B, or subtracting two numbers, which is still always going to be a plus right there. That number is always going to, that character is always going to be a plus. Well, your total resultant error is a standard deviation. It's a sigma value. So you'll see books write this as a sigma, you'll see books write it as a S. I think I've even seen individual books write it as an S in one chapter and a sigma in the next. We had a book that we had to drop at one point because it was completely inconsistent. And these individual ones, those are sigmas too. But that's the sigma for A and the sigma for B. That's your plus or minus. That's your margin of error in a volume that is printed on the pipette. It is the value that your balance tells you. I can weigh this mass plus or minus this amount. Okay. So, not unstraightforward, but not overly complicated. We had the conversation the other day of it's not just the root of the squares, because if it was just the root of the squares, then there would be no point in doing it. You've got there's an add in the middle. Okay, it's a wee bit more complicated when you multiply or subtract. Not multiply or subtract, multiply or divide. Okay. If you multiply or divide, your total resultant error is dependent on the quantity that you are actually measuring, on the size of the quantity. So when you're adding and subtracting, and we did an example, I added two numbers together, and I found the sum of that number. And then, separate to that, I found the error inherent in that value. Okay? So I had to do two calculations. I had to find what the sum was, and then I had to find what the error was. Did I have to do them in that order, in that sequence? I could have found what the error was first, and then come back and found what the sum was. Not when you're multiplying. When you're multiplying or dividing, the actual underlying quantity is part, component in the transmission of the error. Now this is written in a slightly confusing way. I'll show you. In the table that we gave you as this is the volumetric class, right? It says, here you go, that when you add or subtract, and I'm just going to add an A and a B, you can see that the final error is the root of each of the individual errors squared. Okay. And when it comes to showing me multiplying or dividing, it says that the error divided by y is the root of all of the individual errors squared once they're divided by their individual amounts. Okay? So the individual amounts that are in the calculation, the A and the B and the C, carry into it. And then this y. I'm going to move that y over to the right hand side of this equation. Okay, y being the answer. Okay. So y gets to be my underlying value. So if this is just A plus B equals, you want to call it y? then the total resultant error in Y is the error in A squared plus the error in B squared, all squared root 2. Okay. So the total resultant error sigma in Y when you multiply two numbers together. Okay. So A times B is now equal to Y. Is my underlying value. I'm not going to write it out that way. I'm going to write that as an annotation. So Y times the square root of the error in A divided by A squared plus, and it doesn't matter, plus the error in B divided by B squared. So this is a bit more work. This is a bit more work. Let's look at the one that we gave you as a work example. Dissolve 8.506 grams of sodium nitrite. What's the chemical formula for sodium nitrite? Nitrite. Okay, what's the chemical formula for sodium? Na. And then nitrite is one less than nitrate. What's the chemical formula for nitrate? NO3 minus, so it becomes NO2 minus. So chemical formula for sodium nitrite is NaNO2, and it has formula mass that is equal to 68.9953 grams per mole. And it says that we weighed it on a balance that has a tolerance of plus or minus 1 milligram. And we made it in a volumetric flask that had a tolerance of plus or minus 0.08 milliliters. Okay. So dissolve, I'm going to add the plus or minus. Plus or minus 1 milligram. This is in grams. How is 1 milligram represented as a gram? How many milligrams in a gram? 1,000. So 1 milligram is 1,000 of a gram. So if I can measure, my balance can measure this to 1 milligram. How many grams is that? So I'm going to dissolve that up to 100 milliliters. And the volumetric flask that I'm using has tolerance, has associated error of 0.08 milliliters. Okay, so I have to do a couple of things. Here's what I know from general chemistry. That moles is mass divided by formula mass, and that molarity is moles per liter. Ooh. Okay. So let's look what I have to do. You can either put all of this in and do it dimensionally, analysis thing, and put all of the functions. So I'd find moles mass divided by formula mass, and then I would have moles on the top, and then I could divide by liters. Okay. So that, all of this together, so molarity, if I do this as one big calculation, is mass 8.506 divided by 68.999953. That's a gram, and this is a gram per mole. So when I divide, I'm going to put these lines in red. Oh, that's a division. All right, so that makes a division. Grams divided by grams per mole, I get an answer in moles, and then I'm going to divide that by my volume, but my volume needs to be in liters, so I need my 100 milliliters, and I'm going to multiply that by a conversion factor that gives me this in liters, that 1 liter is 1,000 milliliters. Oh, the values don't have to be in red, but the actions should be. Okay. So we're dividing. We're dividing and multiplying. So end up using this formula to find out what my total resultant error is. But it involves knowing, I have to first know what the concentration is. Okay? So the question is, what is the molarity? .506 divided by 68.9953 equals a number. That's your number of moles. And then divide that by 100 milliliters is a tenth of a liter, so 0.1. Okay, it gives you an answer. What does that answer come out to be? So I look at this and yeah, you know, what's the smallest number of significant figures? It is the 100 milliliters. That's a measurement. That is a measurement. It was not given to us as 100 point. Actually, it was 100 plus or minus 0.08, actually. Yeah, so I actually, this kind of says there's more to that number than you were thinking about. Yeah, so I'm gonna go with that. That's my limit right here. I'm gonna limit myself to the 4. It's deceptive. That is deceptive. Certainly without this tolerance right here, that's 100. And 100 written as a number is one significant figure. 100 written as something off a volumetric flask gets the dot. Okay, that is 3 significant figures because you have measured the 0 and the 0. You've measured that. So we get the decimal. But then this tells us, oh no, we know that one for sure. We know that one goes up and down. All right, this is my underlying value. That is Y. That's what you put in here. So if I want to find what the error in my answer is, I go back into the question and I find the things that I used in the question and I write their tolerances in, and then I square them and divide them by themselves, and then I take the root of everything and then I multiply it by the underlying value that is in the question itself. Okay. So I have 2 tolerances. This, let me clear the board a little bit. This is 1.233 root of, okay, what's my first measurement? My first measurement is plus or minus 0.001 gram. Put a note to myself at the bottom that that's for the grams, so when I come back and read it, I don't know that I really need the units in this because this is not, my answer is a dimensionless quantity, right? It's not going to have a dimension, but this is from the grams. I'm going to put a little note to myself so that it says where it's from. It's from the grams. And then the number that goes here we didn't break that number out. We did not break that number out. Okay. This is why I always do everything. I never do things in terms of a dimensional analysis. I always do the first chunk and then I do the second chunk. If we had just said 8.506 divided by 68.9953, right? That's my number of moles. What was that number? Grams divided by grams per mole equals moles. What is that?
0.12.
Yeah, that is 0.123. Okay. And then, if I take the volume and I did the liters is milliliters times the conversion factor, I would find that that was 1 liter. And this is 0.12. That's your last action. It's like being a referee again. It doesn't matter everything that came before you in all of the chaos that happened in your calculation. What was the last thing that you did? I took that number and I divided it by this number. That number has this error inherent in it. And that number has this error inherent in it. So I'm going to take this error and divide it by that number, and then square it. And I'm going to take the volume I said milliliters, right? Let me read the question. Tolerance of 0.08 milliliters. Okay. Spread it. Let's look at those numbers to see if that's important. Smaller number divided by a slightly bigger number, and a very small number divided by a slightly bigger number. I'm going to square them. So those terms are all going to become small, and we're going to take the root of them and then hit them by that number. So I don't know that there's a great deal of consequence here in what these numbers are, just based on their size. I don't think that there's anything in our tolerances that say they are really having a lasting impact on what the value is. Okay. What you come up with? Yes. Yeah. All right, so, 0.6. Is there another 0 here? Is it 0.9 or 0.09? 0.9. Okay. So then, what is your final answer go? Your final answer is that you are 1.233 plus or minus 0.98. Yeah. I think we might need a 0 in there. That seems a bit big.
The first number squared, I got, I guess in science computation would be 4.37.
Yeah.
really, really small.
Yeah.
The second one I got 0.64. That's it.
Now, do I need, there's a question of, do I need to put an extra zero in that because of the milliliters to liters? I'm going to leave it, but yeah, I think I've got a conversion factor. Because of the conversion factor, I think we can actually squeeze another zero in there. And all that does is it puts a zero here. Because of the, because that's still in milliliters, not in liters. I think I really needed to squeeze a zero in there. Right there. And 100 milliliters, which is a tenth of a liter. And I think I needed to put a little conversion factor in there. Oh, that number. Okay. I'll give you a couple of worked examples so that you can follow along and then predict along as you go and make sure that we do this right. But that seems like quite a lot of work. And I think that I'll give you the worked examples that I have. Sometimes you do step by step by step by step, and you do absolutely everything along the way. I've got a bunch of them. I'll share them. All right, let's have a quick run through of some buzzwords that we need about methodology before actually looking at some chemistry, because there's a little bit still to do. We haven't actually used, I've said this word out loud, but we haven't really mentioned it, haven't defined it. What is analytes? That is the chemical being analyzed. Okay. Now, sometimes the chemical being analyzed is in solution with something else or in a mixture with something else, and those other else's don't get in the way of your analysis. In which case, we would have specificity. We would be able to specifically see this thing. And then other times, the other chemical objects that are occupying the same space as it in solution or in a mixture get in the way. So we have the analyte itself, we have its surroundings, which we don't often talk about, and then we have contaminants that get in the way of us specifically looking at this, okay? Because if I have, here's a beaker, if I have some sodium ions dissolved in water, I don't consider, if I'm analyzing the sodium content in here, I don't consider the waters to be contaminants. They're part of the whole chemical system. But if I'm doing a test that's looking for sodiums, and I'm doing that, like maybe measuring its conductance, conductivity, and there's some potassium in the way in that solution as well, that's a contaminant then, because that and this are both registering the same signal. They're in the same group, they carry the same charge. So if I'm measuring charge, I'm measuring both of those. if I am looking at this from some kind of chemical perspective of, well, all sodium salts are soluble. So if I throw a certain amount of sodium at an object, it will make a certain amount of it dissolve. Well, so will potassium. So these will both generate the same response, the same signal. All right, so what I'm looking for is specificity. Specificity or selectivity is another word that you could use in its place. Equals a method that detects only the analyte. Okay, and the more specific we can get, sometimes that's a good thing. Sometimes it's a good thing. And sometimes you don't want specificity. Sometimes you want to calculate all the ionic content that's in solution. So you'd want to count the sodium content and the potassium content. You want a ballpark of everything that's ionic in solution. In which case you wouldn't be looking for a specific test. You wouldn't be looking for a selective test. You wouldn't use a sodium selective test or sodium selective electrode. You would use a pH meter that would or a conductivity meter that would measure everything. Specificity and selectivity are the same thing. And then here's the other thing that we are going to want to look at is sensitivity. And I'm using the word response to allow for everything, which means your test could be a color change. It could be an indicator that changes color in the presence of, anybody taken a COVID test? Yeah, I bet you have, right? Do you get the one with the little reservoir and you put your sample in it? You took the.
Yeah, we did this once.
How do I do it? You swab and then you put it in a little solution and then you pour the solution in the thing and it moves up, it does a chromatography and there's a color change. Okay, well, how sensitive is that color change? How much analyte do I have to scrape out of my mouth before the response, which in this case is a color change, but in a different type of experiment could be an electrical impulse, could be a signal. So all I'm saying is response. How much do I need? Okay. If it's a numerical answer, and you graph all of your data, we can actually quantify the selectivity of a method. The selectivity of a method is 3 sigma divided by concentration. Okay.
So that's a good example.
Oh yeah. Anything that's going to give you a quantifiable number and you can plot it. So if data is plottable, and if you have plottable data, you should plot it. You should. Because your brain's as good as, you know, that software that puts the least squares fit through a a scatter graph, your brain's easily as good as that. Okay. Before we had computers to do that, as an undergraduate, I was taught with a sharp pencil on a piece of graph paper to plot everything out, and then your human brain sits there for 15 seconds with the ruler and just goes, no, a little bit to the left, a little bit up, a little bit down, boom, that's the answer. And it was oftentimes right there on what the computer agrees with. Your brain's good enough to see that. Your brain is good enough to see, I don't trust that single point over there. If I got rid of that as an outlier, it would make the rest of my data look consistent. Okay. So if you have data that is plottable, go ahead and plot it. Sensitivity is 3 values of the standard deviation divided by the concentration of the sample. Which tells us that there is a point at which the method is not sensitive enough to measure what it is that you want to measure, your analyte. We're going to call that a detection limit. Yeah, there you go. Now that I've said it out loud, your detection limit is 3 sigma over concentration, because of course that makes complete sense. Your selectivity, I haven't got it written down. Your sensitivity is the steepness of the slope. So I remember now. It's okay if you get there eventually. So if you can plot your data, all right, so I'm plotting concentration versus response, okay, and I do 2 different experiments. And the first experiment, when I change my concentration just a tiny bit, the needle goes off scale on the instrument. Wow, that's sensitive. Okay, that's sensitive. First, I do a big concentration change, and my color change only happens very gradually, very slowly, doesn't come in. My electrical gizmo that I'm measuring something with doesn't give me a big response. This is now insensitive. So I knew after I'd written it on the board that I said it too soon. Response versus concentration is the slope, the steepness of the slope. Our detection limit, this makes sense because is the lower boundary of analyte concentration. We have a slope, if we have a sample that has a distribution of answers, then at some point we don't have the sensitivity to see this number down here that is so small. Okay. So yeah, I can measure that. I got all the confidence in the world that I can measure this. Starting to run out of confidence now, and at some point some point, I'm going to say, I'm not sure I can really see that. It's in the noise of my signal. I'm not sure I can see the change. And that lower limit, that's just 3 sigmas divided by the concentration. There you go. That makes a lot more sense. Okay. So how do we go about finding that and knowing that what I'm looking at is reliable and unreliable? Is that we use a blank. That this detection limit is the point at which you say, if I give you a sample and it contains the thing that we're looking for, it contains plutonium, dissolved plutonium, and then I gave you a blank, right? So, and we're going to talk about what the blank is in a minute. So this blank is just, let's just pretend it's just distilled water. And you test this and you go, well, I don't see anything. And then you test yours and you say, I'm not convinced I can see anything in that either. When the blank and the sample are undiscernible, then you have reached your limit of detection. Okay? But if I give you this and a blank, this one goes, even the shade is like a little tiny bit of green or pink or whatever it is that we're doing a color change with, or this is just a signal, and this one doesn't give it, the blank doesn't give it, then you've got a signal. Okay? Now, it might be deep in the noisy part of the signal, way out, not way out, but out fringe. Okay? So we're going to use a blank. The lower boundary of the analyte concentration that is detectable, or I'm going to use this word again, discernible from a blank. Okay, so let's say that while I was down on the nature preserve at the weekend, I accidentally spilled some of the plutonium that I had in my pockets into the preserve. And now you want to test, is the water in the preserve contaminated with radioactive plutonium, right? You go and take a sample. Now you need to give me a blank. What's in the blank? Water from something that is reliably similar, okay? So if I'm measuring water from a contamination site, I measure water at the contamination site, and then I measure representative water maybe at the source of the spring just before it gets to the contamination, or way over on the other side of the lake. Okay. Or if that's not available, if that's still not good enough, at the lake across town that is similar, okay? Because I have to take into account, is this seawater? Is this fresh water? Is this water high in iron, like our water is, because it comes through those minerals? So where has the water been? So our blank can be multiple different types. One is it's just pure distilled water. or it is pure alcohol or solvents, whatever solvent we choose from the stock group. Or it's what we call a field blank, that it is similar in every way to the thing that you are testing, except for we're pretty confident it doesn't have plutonium in it. Okay, if you're testing for plutonium, you test it against something that you are confident is similar to the thing that you're testing, except it doesn't have it. Okay, so if we're in a factory and you are making paracetamol, right? Making paracetamol, and you make paracetamol and they shoot down the line in little pills all day, all night, 7 days a week. You take a sample, you just put it aside. You take a sample, you put it aside. You take a sample, you put it aside. And then Dwight comes on at 1 o'clock in the morning and he's been drinking and he makes an error and he presses the alarm button to say, I've done something wrong. Well, now you can test his batch that's coming down the line against the 5 or 6 batches from earlier in the day. And you can see what did Dwight dropped his burrito into the paracetamol making machine, right? And so now you want to know, do I have the contaminant in there? And you've got something to test it against, because during the day you took representative samples of what it's supposed to look like, except it doesn't have refried beans in it. We've got a couple of different types of blank. A blank is a representative sample. I've never met anybody actually called Dwight. They do exist, but I've never met anyone called representative sample. Except it contains 0 analytes. Okay. And we have 2 specific types of blank that are called method blank and field blank. And a method blank, you know, if you're all too young, but there was a case, gosh, it was the 80s, late 80s, early 90s, where somebody poisoned Tylenol before the bottles were secure. So they went to the supermarket, they got some bottles of Tylenol, and then they took them home and they poisoned them and put them back on the shelf. And then they told the manufacturers of Tylenol, I've poisoned the Tylenol. I want N million dollars as a ransom, otherwise people are going to die. Okay. So now it's your job to sample. I've got a bottle. I'm a concerned parent. Is this bottle contaminated? Your blank is a method blank. It contains everything that's supposed to be in the sample except the thing that you're looking for. And the thing that you're looking for is cyanide. That the poisoner had put cyanide in the Tylenol back when you could take the little caplets and open them and mess around with them and put them back together again. And the bottles weren't secure. They didn't have a foil lid on them. So you could just open them, mess with them, and put them back on the shelf. That was the game changer, that one. Or method blank, if you do it environmentally, it's called a field blank, where if I want to measure the impact of a chemical spill, I measure upstream from it. You just measure upstream, because upstream, the water has everything in it that I'm expecting it to have downstream of the contamination site. Oh, got to talk about one more thing about graphing. Yeah, it's your control. I don't know that too many chemists say control group, but yeah, that's what it is. All right, let's talk a little bit about graphing, because we're going to infer information one of two ways: interpolation and extrapolation, right? So just got to make sure that we know what's going on there. Because one's easier than the other. They both seem like about the same amount of validity, but one's better than the other. If I plot response versus concentration, and a lot of the things that you did in chemistry 2, you did a couple of experiments where you put them in the colorimeter and you measured the difference in absorbance over time. And absorbance follows the Beer-Lambert equation, where concentrated solutions are darker than dilute solutions. Okay, so I could, if I know that I have to find what the concentration of fruit juice is, I say, here's a sample of fruit juice. Tell me what its concentration is. You could take a highly concentrated sample of fruit juice and get a big colorimetric response out of it. And then you could dilute it in half, and then you could dilute it in half, and then you could dilute it in half. And if the world is shining down on you nicely that day, you get a straight line. Beer-Lambert equation is supposed to be linear. What's that called? What have I just made? From known standards, calibration curve. I am confident that this is the response that the instrument gives me, or the technique gives me for known concentrations. And then you take your sample and you measure it. Your sample is there. It gives this response, and you measure across and down. And that's your concentration. That's interpolation, because your data point is inside of the data set created by the calibration curve. But what if the calibration curve looks like that, and the sample that you submit gives you a response here? Now what you have to do is extrapolate outside of the values that you are certain about. You are certain that those are linear. But you're not certain that this part is linear at all. Because what if the curve, you know, what if the shape of your calibration curve is actually like that? What if that is the response? Now, for concentration and Beer-Lambert, that won't happen. But I'll tell you what, gases and liquids have curves that dip and then go back up again. So if we were measuring vapor pressure above a solution, and we only measured this part, we would think that that behavior is linear. Well, when you do the full experiment, you find that this thing goes around in a big U-shaped curve, right? So when my sample says I have a value here, well, which side of the calibration curve am I going to hit that on? Am I hitting it here, or am I hitting it there? Okay. So extrapolation's a little bit more dicey. Depends on whether the method really tells you whether or not you have linearity. But there's something else you can do. There's something else you can do. If you have uncertainty about your sample because you have to extrapolate the data, here's what you can do. You build the calibration curve after you've taken your first sample. So here's my sample, and I don't feel confident about it. So here's what I'm going to do. This is grape juice, right? I want to measure concentration of grape in grape juice because I don't want to put too much grape in it, and it costs too much. That's my sample right there. So what I do is I go to the stockroom and I find a standard grape juice sample, and I add a known amount, and it bumps my value to here. And then I add another known amount, and it bumps my value to here. And then I add another known amount. And now I have every confidence in the world what my original value was. Okay? That's called standard additions, where you, if you have uncertainty that your information's not great because you're not interpolating anymore, you take your original sample and then you just add a little bit more. But you're confident that you know the mass, the volume of, the concentration of, and then you add a little bit more, and then you add a little bit more, and then you add a little bit more, and boom, you've built your own calibration. Those are standard additions. And the other thing that we can have, that really I'm going to leave until the instrumental course. Right here we've got an NMR. And the NMR scale runs between 0 and 10. The frequency scale is called parts per million. But our samples, and this is one that's delivered to us from the factory, this one is sealed. Right? There's a little tube with solution in it, and it's factory sealed. So nothing's getting in and nothing's getting out. No contamination to this one. There is a tiny drop inside of here of an internal standard. So I can't remember what this is. It's water or alcohol. I can't remember what that is. But it has a tiny little speck inside of it, something called tetramethyl silane. TMS has an NMR signal exactly at 0. so if it's a particularly hot day and our magnet was to drift in its field strength, then we would notice that the internal standard in this sample wasn't reading at 0 anymore. We would just dial it back as an internal standard. Okay. I think that's a lot about measurements. Now, looking at, did you each got a copy of the book?
Yeah.
Okay. The book has a number, so like the first 5 chapters are a lot about Excel in there, which is good. I'm fine with that. But then there's like, hey, here's a little tiny worked example. Here's a little tiny worked example. I'm going to collect a bunch of those, write them up, and then ask you, look at this calculation, now do another one. Okay, and we're going to go through that, and I'm halfway writing a quiz with buzzwords and whatever. We're going to do some calibrations next time in lab to make sure that the glassware that we're using equals what we're expecting. It's time to talk about chemistry. It's time to talk about chemistry because we're going to look at solution concentrations of acids, and we're going to find limits of precipitation to get valuable metals out of solution. And all of that is equilibrium. All right. We've got a few minutes to go. 7 minutes. Tell me everything you remember about equilibrium. It's a balanced equation. If you catch someone coming out of middle school science, they say it's reversible. That what's here and what's there are reversible. That's a little bit too simplistic for any survey of equilibrium that involves numbers, because it's not reversible in the sense that I can take all of these reactants and turn them all into products, and then at some point later turn them all back into reactants again. That's not equilibrium. Equilibrium is something different. That is a truly reversible reaction. Okay. Reactants on the left, products on the right. Do all the reactants turn all the way into products? No, because if they did, we would use that symbol instead. So the reaction stops part way? Is that what's happening in an equilibrium? Is it stopping halfway? Does the concentration of reactants equal the concentration of products because they're balanced half and half? No, it's not that either. That's too simple. So it's not equal. How about the reactants go a certain percentage and then they stop? It's getting closer, but I don't like that word stop, because the equilibrium is dynamic. It's not static. That means that the equilibrium settles on a value, like a percentage completion, that I'm going to take 60% of my reactants and turn them into products. And then I'm going to settle down at that number. But at any point, a product could turn back into a reactant. And when it does, I'm not at that 60% mark anymore. So for every product that decides to turn back into reactants, a reactant has to turn into a product. And you get this churn that it forwards equals backwards. So the equilibrium happens when the forward reaction and the reverse reaction equal each other. So it's dynamic. My abbreviation for equilibrium is EQ with superscripted M. Okay. How do we measure reaction rate? What quantity, how do we quantify a reaction rate? We have a rate constant. Remember this thing? It was called a rate law. Remember rate laws from kinetics? I might do a tiny bit of kinetics. I'm doing kinetics now. What does the rate law say? The rate law for anything says that the rate of reaction is equal to a constant, it's a lowercase k, times the concentration of something. Is that the concentration of products or the concentration of reactants? I want to know how fast a reaction is working. Do I measure, does the reaction's rate depend on its reactants or on its products? This is a very, very logical question because the products haven't been made yet. So how can they possibly have any influence on how fast the reaction is working? This has to depend on the reactants, okay? So my forward reaction has a rate constant that I'm going to call, I can call that F. I can call it forward. Guess what the reverse rate is? If I look at the rate in reverse, then I'm starting at this side and going back, right? So in reverse, I start with the products. The rate constants for those two are equal but opposite. And one has reactants and one has product. And we're going to invent a new symbol, K. That's an uppercase K, which is our equilibrium constant. And it says, dynamic equilibrium occurs when the rate of the forward reaction is equal to the rate of the reverse reaction. The forward and reverse are the same. That the rate going forward and the rate coming back are the same as each other. So K1 and K minus 1, when I divide them, gives me, this is going to move over the equal sign, and that's going to move over the equal sign. Products over reactants. Next week, we'll look at finding an equilibrium concentration. You've all done that before, multiple times. And then doing it more accurately. Knowing when you can use a couple of rules that are assumptions and make your calculation easier, and when you can't do that and you have to do it the long way. The long way is a quadratic solution. Your calculator knows how to solve a quadratic equation. Your calculator or your tablet knows how to solve the quadratic equation. You can either do it the long way by hand, don't do it the long way by hand, or you can just have your calculator do it for you. Okay? That's okay. See you Tuesday.